boys and girls, welcome back. Happy Tuesday. So in this video, I'm going to be reading our anthology story, which is called A Drop of Water by Walter Wick. Before I start, the genre is expository text. So we discussed this genre already in class. This genre is basically going to explain something to us. So we'll make a prediction really quickly. You can pause the video to take some think time about what you think the story is going to be about. And also, we're going to review our essential question: what can you discover when you look at something closely? So the reason that we're not doing any new science lessons is because in all the stories that we're reading for ELA this week, they all have to do with some kind of science. And today we're going to read a little bit more and learn some more interesting science facts like we did yesterday. But we'll get started. So, molecules in motion. If a drop of water is added to a jar of still water, and if the water in the jar is not stirred, where will the new drop go? Will it stay near the top or sink to the bottom? A simple experiment reveals the answer. A drop of blue water enters a jar of clear water. It begins to split up. Parts of the drop sink and swirl in different directions. At last the colored drop breaks into so many parts that it has become part of the whole jar of water. The molecules in the liquid are moving all the time, pushing and pulling each other, attaching to it and breaking away from neighboring molecules. The molecules in the blue drop break apart because they are pushed and pulled all over the jar by other water molecules. The energy that keeps molecules moving is heat. This heat can come from the sun or the room in which the jar is standing. Without heat, water would not remain a liquid. Ice. When water cools, it loses energy. The molecules slow down and eventually stop swirling and pushing each other. When water freezes, the molecules lock together, forming a rigid structure. A drop of blue water no longer moves. The water has changed from a liquid to a solid, ice. Ice is a solid, like metal or rock, but unlike metal or rock, ice is a solid only at the temperatures of 32 degrees Fahrenheit, or 0 degrees Celsius, or colder. At room temperature, ice melts, changing back to a liquid. So, based on your predictions that you made earlier, did that match what the story is about so far? So far we're learning about water and its many different forms. So we learned about solid and also liquid. Water vapor. Water always seems to be disappearing, from wet clothes on a line, from puddles on the ground, and from dishes on a draining board. We say it has dried up, but where has the water gone? Just as water can be a liquid or a solid, it can also be a gas. The water from the wet dishes evaporates. That is, it turns into a gas called water vapor. Molecule by molecule, the water from the drops on the wet dishes drifts invisibly into the air. Heating water in a kettle speeds evaporation. Heat from the stove makes the water turn to steam, which is extremely hot water vapor. When the steam hits the cooler air, tiny droplets form and we see a cloud just beyond the kettle spout. Almost immediately, the droplets evaporate and change back to invisible vapor. Then the water molecules mingle with other molecules that make up air. So we just learned about solid water and then also gas. So what does it take to make water solid? And you can pause the video and think about it. It takes cold temperatures, right? And then to make water a gas, it takes both cold and hot temperatures, right? Condensation. The air around us always contains some water vapor. Water molecules move rapidly through the air and hit everything in their paths. The molecules bounce off most warm surfaces but stick to surfaces that are cold. In these photographs, molecules of water vapor stick to the coldest part of the glass. Gradually, droplets form on the glass as the molecules accumulate. Water vapor changes from a gas to a liquid. That is, it condenses. So where are some places that you can see condensation like this, where you see water droplets on an item like that? Evaporation versus condensation. In the photographs above, why do the water drops outside this glass disappear while the drops inside remain? Outside the glass, the water evaporates and spreads throughout the room as vapor. In time, the drops disappear inside the glass. Water also evaporates, but the vapor is trapped. The air inside the glass becomes humid, which means that the air is full of water vapor, and that vapor condenses back into the water drops as quickly as water molecules can evaporate. Therefore, the drops remain. Remove the glass and the vapor expands throughout the room. Evaporation continues, but condensation slows down. In time, the uncovered drops will disappear. How clouds form. Clouds are made of tiny water droplets, too small to be seen without a microscope. If a cloud droplet is to form, water vapor must first condense on a particle of dust. Carried by wind, these dust particles are often bits of pollen, soot, soil, or salt. This experiment shows how cloud droplets form. Salt is placed on a jar lid above a dish of water. A glass cover traps the water vapor in minutes. The vapor condenses on the salt and coats each grain with water. Hours later, the salt dissolves in the water drops. Clouds form when water evaporates from the Earth's surface and rises into colder air. There, the vapor condenses on cold, airborne particles. More and more molecules cling to the particles until droplets form. It takes about 1,000,000 cloud droplets to make one raindrop. Rain does not taste salty or appear gritty because the particles that allow clouds to form are usually too small to be noticed in raindrops. Snowflakes. This snowflake is shown 60 times its actual size. The angles between the 6 major branches are repeated over and over again in many of the smaller details of this amazing structure. How can such an intricate object form in the sky? Cloud droplets form when water vapor condenses on particles. But in very cold air, water molecules that cling to particles form tiny ice crystals. As more water molecules from the air freeze onto the crystal, they join at angles that allow a 6-sided structure to form. If the crystal grows large enough, it will fall to the ground as a snowflake. Clouds that produce snow often contain both ice crystals and liquid droplets. At the center of the snowflake is a cloud droplet that froze, allowing the snowflake to form around it. Scattered throughout are other cloud droplets that have frozen onto the snowflake as it fell through the cloud. Sometimes snow mixes with pellets of sleet, which are frozen raindrops like the ones shown below. By contrast, snowflakes are ice crystals that form when water vapor changes directly from a gas to a solid. Endless variety. Many ice crystals grow into shapes that are just tiny slivers, rods, or clumps of ice. Of these, the underlying 6-sided structure may not always be visible, but when weather conditions are just right, the crystals will grow into an astonishing variety of elaborate 6-sided designs. All the snowflakes on these 2 pages were photographed on the same day. All share the same angles but vary in design. One has 6 branches of unequal length, giving the appearance of a 3-sided snowflake. Another snowflake has only 4 branches. Apparently, 2 of its branches didn't grow. Odd variations like these are typical because Different conditions of humidity, wind, and temperature affected the growth of each snowflake as it fell. Each design holds secrets of its unique journey to Earth. When a snowflake melts, its intricate design is lost forever in a drop of water. But a snowflake can vanish in another way. It can change directly from ice to vapor. The sequence below shows a single snowflake as it gradually disappears. Frost and dew. On some days when the air is humid, a sudden drop in temperature during the night will cause water vapor to condense on cold surfaces. By morning, the landscape is covered in sparkly drops of water, or dew. If temperatures fall below freezing, the cold weather relative of dew appears as frost. On windows, frost forms along tiny scratches and other imperfections in the glass. As with snowflakes, frost is the result of water vapor changing from a gas to a solid. That's why the angular structure of ice crystals is evident in fern-like patterns of frost. When dew forms, a short walk through the grass will soak your feet. On spiderwebs, dewdrops appear like glistening pearls. In the photograph above, we can see how water reflects and bends light. An upside-down landscape appears in each drop of water and light. If you look carefully at this beam of light, you'll see the mysterious way in which light interacts with water. Some of the light is reflected, which means that it bounces off the surface of the water. But some of the light passes into the water. As the light enters the water, molecules bend the light or refract it. The bent rays of white light are transformed into all the colors of the rainbow. How is this possible? White light is made up of waves of many different sizes or wavelengths. The shortest wavelength, which we see as violet, bends the most. Red, the longest wavelength, bends the least. All the other colors fall in between. Sun shining on a spray from a garden hose creates a rainbow. The spray produces drops of water that bend the light and flash bright colors when seen from the correct angle. Natural rainbows work exactly the same way. The sun must be behind you and low in the sky. The arc of the rainbow is caused by the sun shining on billions of spherical raindrops that fill the water cycle. The sun's heat and the Earth's gravity keep water in constant motion. Water evaporates from puddles, ponds, lakes, and oceans, from plants and trees, and even from your skin. Water vapor moves invisibly through the air, but it is always ready to condense on a cool blade of grass or the surface of a pond. Massive clouds form as vapor condenses on tiny particles of dust in the air. Then, and only then, can water fall from the sky as rain, replenishing lakes, rivers, and oceans. Hard to predict, impossible to control water cycles around the earth. And water is precious. Without it, not a single living thing could survive. No plants would grow, not even one blade of grass. No animals would roam the earth, not even a spider. But somewhere in the world, right now, snow drifts on a mountaintop and rain falls in a valley. And all around us, we're reminded of the never-ending journey of a drop of water. Okay, so today or this week, your skill is sequencing, which is basically putting events in order, right? So this is what your sequencing activity will look like on Skies. You'll have 4 boxes here. Now, we learned about water in this entire story. We learned about how water can be a liquid, how it can be a gas, and how it can be a solid. We learned about the water cycle. We learned about how water can condense or evaporate. Now, your job today is to explain to me, using the information that we read in the story, how that would happen in 4 steps. So remember, you should use sequencing words like first, next, then, last. I want you to focus on those 4 words: first, next, then, last, to describe how water changes. Now, if you want to describe how a snowflake is formed or ice crystal, as it says in the story, then you can do that. And using the information from the story, you'll fill out this chart. I'll copy this chart onto Skies, and then I'll make a drop card where you can either draw this chart on a piece of paper and fill it in, or you can just fill it in directly. Remember, if you have any questions, you can email me, you can message me on Google Classroom or on Skies, and I can help you out with that. Bye!